So, functional programming in Scala. I'd say motivations. I'm a big FP enthusiast, and I would say the four main reasons for these is, at least for me, functional programming allows for easier reasoning. And like if you go in the, let's say, the naming of functional programming, you will see this a lot. Equational reasoning. We'll get to that in referential transparency. Same thing. It's just you can think about your code more easily. I think functional programming allows for code reuse and composition. We'll see that in action as well. It's easily testable. I didn't do that in this presentation, but of course, I'll touch upon it. And then code refactoring, which is like a combination of functional programming and a statically typed language like Scala. Why is it? Okay. So throughout the session, what I'm going to try to do, and I'm going to actually pull my other screen. Wait a second. Can you see my coding screen as well?
Yep. Yes.
Okay. So what I'm going to try to do throughout the presentation is basically a small modeling exercise, which is to build a hockey team, because I came back from Canada and I really like playing hockey. As a first exercise, and without actually jumping to any functional constructs, just to go a bit over some Scala code, and then we'll put some theory around it. Let's try to build a hockey team with the following small. I don't know who is doing a lot of noise on background noise. So what we're trying to do here is to model players. So a player should have a name, potentially a nickname if it's a cool dude from the team. He will have a number and a position, so either offense or defense. We'll try to model a team, which is about like 10-ish players or more, and the team should have a name, basically. And then we can put those, like if you put two teams together, you can actually start a game. So I'm gonna try to do this live in the meantime, explaining a bit the constructs we're using, and then we'll jump into more of the what it entails in terms of construction in the functional programming side of things. Before quickly going there, like the three constructs I'm going to use, case classes, which are in Scala a way to basically store data together. So for example, you could define a case class as a person saying it has a first name and a last name. I'm going to touch about options, which is the null safe way to handle missing data. So it actually is a type that encodes the fact that you might have something or nothing. A bit the same way, like if you look in Python, you would have to see, you would have to check if my thing equal is none, then do this or do that. This is exactly doing the same. I'm saying, okay, my option here, I gave something in there. So I'm actually going to fall in the first case, and I can retrieve the string that I gave as an input and do something with it. If you're unfamiliar, the three question mark notation is just to allow the compiler to work without having to actually implement something. And then none, this is when you don't have anything. Then the other construct I'm going to use are SIL traits. By the way, like because we don't have a huge audience, are a lot of people familiar with these constructs? Like, do I have to go really in detail of how these works and how we're going to use them, or is everybody familiar with these concepts in Scala? You can post it in the chat if you don't want to speak it out, by the way.
For me, Scala is totally new.
Okay, so I'll go through it, and then we'll see an actual example. So what this means, all in all, a trait in Scala is something, it's like a super type, something you can extend. So if you come from a more object-oriented world, this is basically like an abstract class, something you're going to say, I extend this, and you inherit all the properties from it. Another way to use it in Scala is basically to be able to do enumerations. So I don't think you have the same concept in Python, but you do have the same concept in Java, which is an enumeration is a finite set of things. So in this case, for example, I have my farm animal, and a farm animal can only be two things, either a chicken or a pony. That's, of course, you have more farm animals out there, but if I would model my farm, this is something that could look like it. And then when I get in my code, when I get a farm animal, this means it's going to be either a chicken or a pony. And the compiler is going to make sure that I'm handling those two cases correctly. This is because we're in the typed language. So you need to define your types very precisely, which is like one of the main things you have to do when it comes to business, because if you model this correctly, then you gain a lot of nice properties that we'll cover afterwards. So for hockey team, using the three constructs that we have there. So let's start from the player. So a player is definitely, so if you had to choose from those, from the following constructs, a player is definitely the first one. A player is going to be a bunch of things stitched together. So we can say, okay, I'm going to create a finite scale case class, which is going to be called player. The player is going to have a name, maybe a nickname, a number, and a position. So a name, which is going to be a string. Maybe a nickname. So there we're going to use the option type, which means it's maybe there or not there. It's optional. So nickname. A number. So number is going to be an int. You could be more precise, and there are ways to be more precise. We can touch upon that later. And a position. So a position should be either offense or defense. So there, what we're actually going to have to do, we're going to have to define something that is either offense or defense. So we're going to use the sealed trait. By the way, the sealed means that if you come from the object-oriented world, this just means that all the subclass needs to be in the same file. So this forces you from an implementation point of view to put everything in the same file. So not super important. We're going to use a sealed trait, which is going to be called position, and we can have only two positions. So one of them is going to be case object is only, it's like a case class, but it doesn't have anything in there. So when you do that, you create a case object. So it's going to be either offense or defense. Now I can use this inside my player, and so a player also has a position. That's it. So there I've modeled my player. Now that every time I use a player, I'm going to be sure that every type in there is correct, and that's, for example, for the position, it will be only one of the two, either offense or defense. Team name, yeah, I've put over there that we only have two team names, so this is going to be very much the same as this construct. IntelliJ, thank you. So we can either be from the Rangers or from the Penguins. I don't know if you know the teams, those are actual teams. We have to change this type to be a team name. Penguins, I messed it up. All right, that's fine. And then we can define a team. So if we have to define a team, we see there we have two things. So again, a team is the composition, like it's the addition of two elements. So players plus a name. So since that's the case, we will replace the type team, which is just here a way for me to use those types afterwards. So I can define functions on top of them. But when you define the case class or a sealed trait, you're also defining a type in Scala. So we're going to define a case class team. So a team will be will have a name. So actually, the team name is going to be the type we defined earlier, and the players. So players is just going to be a list of player. And then a game is only two teams. So again, composition of multiple elements together. So find a case class game. Let's say left So on the left, we'll have one team, and on the right, we'll have another team. So there we go. There we have fully modeled. So using the very simple constructs, so we only used those 3 constructs, which is one of them putting things together, stitching things together. The other one is really concerning optionality. This is very important because otherwise you end up, it's the same thing in Python, and so in Python it's called none, and in Java it's going to be null, which means if you call something on it, it's going to fail in your code and you don't even know about it. Using a type like this, you actually are forced to handle both cases separately. And the trait here is simply to enable the enumeration of different possibilities. So far, questions? Guys? Are people posting questions inside the... Oh, I didn't start my video. I just saw I didn't start my video.
So far, no questions, Gauthier.
So far, no questions. Okay, good. Cool. So I quickly go, so using these constructs, I quickly go a bit deeper into the Scala type system. So the Scala type system really looks like this. So this is a full overview of the Scala type system. I don't know if people are familiar with this view of the type system. Otherwise, it might not be useful that I go deep into it, because like if not a lot of people have done Scala, it's a lot to take in at the same time. So you guys tell me if I need to skip this section. Nobody. Chat.
Yeah, no suggestion.
Okay, so no suggestion. I'll quickly go over it. If it's not clear, or if you just don't care about it, that's fine as well. So there, what you see here is basically, so it's inheritance. It's the inheritance schema of the Scala type system. So everything is any. So you can, like, if you would put any in here, you could basically fit anything in there. So if I put any, I could have a player, and for the name I could give anything, an int, a short, a byte. I could give a list, an option, or any class that I build. On the other hand, if you go deeper in the tree, then you are refining your types. So we have values, any val, which are definite, let's say in size, they take in memory. So everything that you see here on the left side of the tree is something that is really definite in size. So a double as a fixed length in memory and stuff like that. On the right hand side, you see any ref, which is referencing. So for references, there you can have literally a bit of everything. So for example, lists fit in there because they don't have a definite site, and we're passing them by references. Options or classes you define yourself. Null is in there as well, and null, like an object, like null is always a possibility when you give an object. So if you would have any ref here, you could give null for it, which we try to avoid using option. And nothing, and this is where I want to go. Why would you need this type, which is basically a bit strange, because nothing is everything, but there is no type that is extending nothing. So you cannot instantiate nothing, basically. Nothing is called the bottom type. And yeah, as I said, it extends everything. So you can always put nothing somewhere, but you cannot have something that extends nothing, basically. And an example usage of this is that if you would define an option, like we did, like this is how the option is defined in Scala. None is an option or of nothing. So that way, none can fit anything, because any class you could put nothing instead. I don't know if that's clear, guys. I'm looking at the chat. So if nobody talks, it means it's extremely clear, or people are just eating their lunch. A bit theory about the surrounding that we've done here on the right with our classes and our seal traits. So this is the terminology in the functional programming world. So what we've seen as classes, by the way, tuples is exactly the same construction as a class. So you can see a class as a named tuple coming from other languages, for example, Python. these are called product types. So product types are really stitching together multiple values that have or usually have different types or different properties. And then you have sum types. Sum types are more the counterpart of the product types, which is they are enumerations basically. So they define what can be in a set. So for example, you could have, okay, I want to describe all the fruits and vegetables. And something coming in my basket would be one of the two always. The same way we have done it for position and team name. The team name is going to be either Ranger or Penguins, and the position is going to be either offense or defense. As I mentioned, so in Scala you should use for other reasons that I'm not going to mention here, but you should use seal traits or either. Either is a forget about either. It either is going to be either left or right or something. So it kind of have the same meaning. Like for when you have two values, either can fit in there as well. But okay, I'm actually gonna show either. This is gonna be so. If I define, you could have something that's called. You could have a type called either team name, which is going to be like, and this does not compile. Great. Okay, well, forget about it. That's fine. But usually you use this when you only have two values. Does not work here for some reason. And using these very simple constructs, you can basically define your whole domain on the right. Again, it's just I also want a bit to demystify like all the namings that goes surrounding functional programming. So when people talk about algebraic data types or ADTs, this is actually what they mean, which is what everybody is doing, putting data into classes and enumerating everything that can happen, basically. Why? So in the typesetting, you have to do this. It's not the case for Python where you could fit anything into everything. A good thing, I think, like benefits of types are the following. So you have a precise domain and codomain. I'll get to that later. It's linked to the definition of a function anyways. It forces you to have data correctness. So if you really do this exercise before starting to implement anything that is business logic, it will force you to design your types and to handle, like try to handle all the complexity is going to be encoded in your types, and you will have to deal with all the possibilities every time you use one of them. So if I would use a position somewhere in my code, I will have to specify each of the cases, whether it's offense or defense, and I will have to deal with those if I need to. The types and the Scala, like the fact that it's statically typed, will force you to do this. So as I said, so data correctness, then design and thinking. So yeah, it's going to force you to design your types correctly, because if you have too many of them, or if you don't design them correctly, then it's going to be extremely difficult to manipulate your data. And then we'll see that afterwards, but you can already see it here actually, is that using types and functions, when you describe a function in Scala, so the Scala description of a function is using def, which is saying I'm going to create a new function. I'm going to give it a name. The parameters come afterwards, and then here is the return type. If you see this and you have the types that are defined correctly, then there is only one thing that can happen, right? Like add player, you give it a team and you give it a player, and it returns another team element. Yeah, you know that you're basically going to add this player to this team. You don't know what's happening here. Actually, the implementation is not even there. But you can abstract this very easily for somebody that doesn't need to know how to actually add a player to a team. Like what's happening here is very clear. So generally speaking, I think types are like a higher upfront investment, because you need to do all this exercise before starting to code something. But on the other hand, you give, you have a good return on investment in terms of a description of what's happening and people coming to your code. So far, questions?
So I have a question.
Yeah.
So I know nothing about functional programming, but I see that you're using final case class, for example. What does it mean that it's final? Because if you have a team, you can add players. So in what sense is it final? That you cannot add other attributes, or what?
No, exactly. So final here is, yeah, that's totally right. I did not explain this. Final only means that you cannot extend this case class afterwards. You cannot have a subtype of player. That's the only thing it means. You like, this is also going to work, but then I could have, and this is very discouraged by the Scala programming language. You could have yet another case class saying, I don't know, for example, you could do this, all right? I mean, you would have to give some parameters there, but if you put final, this is not permitted. You cannot do extends here, which forces this so this in combination, so the final in combination with sealed, for example, forces you. So sealed is going to force you to put everything inside the same file, and final is going to say there is nothing else that is going to be implemented like subtyping this, which means if you combine those two, you know that everything is in this file, because it's not possible to have something else than this, like a subtype of defense does not exist. And on the other hand, you're forcing all the definition of the subtype of positions to be in the same file. Does that answer the question?
Yes, and more. Yeah, thanks.
So to go back to our modeling exercise and to code a bit, let's do those three functions. So I want to be able to add a player to my team. I want to be able to remove a player from my team. And I want to be able to switch one player, so player one for the other, okay? So if we go to implementation, there is not much that can be done. So if you see that the team is basically a team name, so the team name is going to stay the same, like and you want to add a player, you are adding a player to the list. So what you're returning here, by the way, Scala doesn't have return statement, so you don't need to do this. The last statement is always the one that is returned. So we could simply do t.copy. Well, okay, let's do it. Let's create a full new team first. You could use copy in this case, which is a way to copy everything but the same. So up that name and t.players. So that's it. That's the full implementation of the add player function. So here what I'm doing is I'm saying, okay, I'm gonna create a new team, because something else that is a bit imposed by functional programming is that you don't change your values. So compared to functional to object-oriented programming, where you would basically just replace this inside your class, here we're creating a new one, so that the input team is not changed. And this has very nice properties. We'll get to that later. So I'm creating a new team, which takes the same name, because this is actually in this context of the function, only this name is available. So I could not take it from anywhere else than this team. And then I'm adding a player. So I'm taking the same players I had before, and I'm just adding one at the end. Now on to the remove player. So we're going to do, the start is going to be the same. So we're going to use also the same name, because we don't have any other name. And then we want to remove this player. So let's say that the player is fully identified by his name, for example. So I can here say, I'm going to take my players and I'm going to filter out. So yeah, you could use filter not, but I'm going to make taking a player if the name Okay, am I missing a parenthesis? Yes. Okay. So what I'm doing here, okay, I'm maybe gonna pull that out so that it's easier to read. So what I'm doing here is I'm looking at the players that I have in my team, and I'm filtering. So filter takes is going to ask for a function that, given a player, in our case, because it's a list of players, is going to return a Boolean whether or not it needs to keep it. So I'm just comparing to the player that I have for this name, and I'm going to say, okay, if I have the same name, then return false. So basically remove the players that have this name. This is not, as you can see, it's not the best, because if you would have two players with the same name, this would break, but we assume here that the player is fully identified by his name, and that you don't have two of them. We could use, for example, I don't know, the position or the number of the shirt, which would probably be actually better. And then taking this new list of players, I'm recreating a new team object with the same name, but my new players. And now on to the last function. So maybe without me actually just doing it, like, can someone tell me how you would implement this, knowing that we already have these two functions?
Are these objects sort of immutable? Do you need to would you need to return? Oh,
Yeah,
okay.
so
No, I just understood. I thought taking one player from one team to the next, but I got it.
no, really. So here, yeah, this function, what it's trying to do is take from a team, remove player one and add player two.
So what you just said, basically.
Thanks. So yeah, there we're gonna do the same.
But can't you use just the two functions?
Yeah, so that's what we're doing. So we're gonna take remove player, and we're gonna take team T P1, and I'm gonna show a better way to, like, a nicer way to write this in Scala. But let's say and then so here I'm doing, like, removing one player and then adding the next one. Another way to write this would be to use function composition. So in Scala, you could basically take the first function and the two functions, put them together and create a function that only does that. I'm not going to do that because it's going to be a bit verbose, especially because the code is not made to do it so easily. But that's something you can do. So here, what I'm trying to show is really that you can easily compose functions, and because you have immutability, you can very easily pipe stuff from one instruction to the next. Yeah, questions on this? Okay. So on to functions. So putting a bit of theory around it. When we talk about functions inside the program, like functional programming, as you can guess, it's pretty important. So what we're trying to do is use, like, coming from the mathematical sense of functions, we try to have three properties inside functional programming, which are the followings. Totality, which is a fancy word to say that when you give something from the input, which is called the domain, you will get an output, which is called the codomain, that is part of this domain. So let's say here I'm giving in teams, a team and a player, and it's returning a team. So always when I will give a team and a player, I will return a team. Always. There is no other way. Determinism. Determinism, which is saying if I give two inputs to my function and these inputs actually are the same, then the outputs will be the same as well. And this ties in with immutability, because if we would have like kind of in Python or in object-oriented programming, where the function starts to change things that are outside of its scope, then you cannot have this property, which is why we're always doing a new team here, so that the team that is here does not change. So immutability is really tied to determinism in this case. And no side effects. This is because Scala has a bit of a caveat in the sense that you could do anything in here that would break this no side effect, which is like having a side effect is doing something else than actually evaluating the function. So if I only simply do this, which we all do at some point to debug our code, I'm producing a side effect. I'm not only computing the return team, I'm also printing stuff out, and there is no way from this type signature to know about it. So nobody, like if you don't delve into the code and if you don't go into the implementation, you cannot know that this is going to print into the console. And if you expect clean logs and stuff like that, this is going to break. So if you use only these functions, these are called pure functions in the sense of functional programming. This is very much tied to mathematics, as you can guess. And then aside from using pure functions, which I've called mathematical functions, there is a safe, because Scala is a dual language which has a lot of object-oriented programming baked in. You could very well program the same way you do it in Python or in Java using Scala, because Scala also has var, for example, where you can switch the content of a variable and stuff like that. So if you use val, if you use only pure functions, type reflection I'm not going to touch, and if you don't have null, because null is basically can extend every class. So instead of returning team here, I could very well return null. This is going to work, but if you do this, then the person on the other side of this function, which is using it, cannot know that it can be null. If you wanted to do this, you would need to use an option, so that the person outside of the function can see, okay, sometimes I'm not getting a team. For example, I don't know, if I have too much players or something, this breaks. Benefits of pure functions. When you do this exercise of actually using only pure functions, only returning what you're supposed, like only computing what you're supposed to return, then your function signature really gives it all out, because there is not much that can happen in this. When you say I'm going to add something, I'm going to add a player, well, you're obviously adding a player to the team you're given as an input, and you're returning a new team with that player added to it. Composition, so we've seen that. Switch is only composing two other functions, which is add and replace. So having small blocks enables you to build them very quickly. And the person implementing switch doesn't need to know how add and remove are implemented, because it's safe from the outside to use those. I've already mentioned it multiple times. It gives control back to the person that calls the function instead of the one that implemented it. So when I take remove player, it's not doing anything else than removing the player. It's not changing the values that I give inside it. It's not returning something else than the team. So I'm sure I can safely use this, and I have no reason to actually go in here and look at, oh, it's implemented, unless, for example, for pure performance reasons. And this, like, as the way I touched it at the beginning, this is what we call equational reasoning. So here I'm really treating every function application as an equation. So I can really say, I can really abstract this, and I can say, okay, removed is now the result of this, without saying it's going to change the value of t or anything. It makes it so all these properties makes it easily testable, because if for the same input and for you get the same output, it makes it easier to test, basically, because you can have tests that are always either failing or not failing, depending on what you expect. Before jumping to the conclusion, is this clear for everybody? I'm guessing that's a yes. I'm just going to touch quickly on what we've seen and basically where you can go from here if you're interested in more topics. So what we've seen is algebraic data types, which is a fancy word to say composing and describing your domain, which is extremely important in functional programming and type languages. We've seen how to build and compose functions. And then I'm quickly gonna demonstrate this. So why is it so that people always say, yeah, it's a nice mix between object-oriented and functional programming? So I'm gonna show this. So we have these functions, right, which is add player. So what add player does actually, add player is acting on the team. So instead of having this, notation, what we could have is here, because it's a class, so object-oriented construct, I could very well have this definition fitting inside here, and I don't okay. What am I doing wrong here? Result simple players. Alright, this should work. Wait a second. Demos. Oh, it's because I have not imported my classes. Ugh. Okay, this is just, anyways, I would need to move stuff around a bit, but the idea here is that we get for free. So I'm gonna remove the implementation. It's not so interesting. It does the same. For free, I get the dot notation. So what happens is that if I also do this for remove player, so like this, and I would change the implementation accordingly, then the nice thing is I can do t.add player p1.remove player p2. Yeah, that's it. So this is taking, so this notation that you see here is really putting the methods, so they are called methods and not functions because they are inside a class. It's putting them in the class so that you gain this notation, which is not sacrificing any functional property. It's just a nice notation on top of it, which is why a lot of people are referring to Scala as a FP plus object-oriented language. And if you go from here, you can go a lot more crazy on the types. So you can add basically polymorphism, which is a way to add like not defined types in advance. It's like functions on top of types. Monads, modeling effects, because this is a very simple example, but as you can guess, you do need to go in the database for real applications. So how you do this in Scala is going to be by defining the effect inside your types. And optics, I'm not going to touch anything about that. Like, do you have questions on this? Yeah, that's it then. That's really it. I see I'm a bit over time as well.
Yeah, okay, thank you, Gauthier. There are no questions in the chat either.
I see.
I've recorded your session, and so I will be posting it in the meetups as a link, and it will be on our YouTube channel. I think it's. I will watch it again to get everything.
Yeah, sorry. I know it's a lot. Yeah. By the way, I figured out what was the issue here is that I was adding the methods inside the player class instead of the team class. So which is why now it's actually working.
Yeah. Okay. But still, if there be any questions, they can be also posted on the page of the video. So okay, thank you, Gauthier, for
thank you guys
enlightening us on functional programming, and thank you for joining us, and hope to see you again. Bye.
Bye.